Welcome to The Explainer. Today, we're going to pull back the curtain on the incredible technology that lets doctors literally see inside the human body. We're talking about demystifying the whole world of medical imaging, from X-rays all the way to MRIs. Okay, so picture this. You're in that hospital gown, you're waiting for your scan. Let's just start with the one question that is on pretty much everybody's mind. Is this whole thing safe? Well, to really answer that, we have to split the entire field of medical imaging into two big teams, two fundamentally different groups that work on completely different principles. On one side, you've got the no radiation zone. These are methods that are totally safe for everyone, including during pregnancy. And on the other side, well, you've got the radiation zone, which uses a type of energy called ionizing radiation that needs to be handled very carefully. So, in the no radiation corner, we've got ultrasound. This thing uses high-frequency sound waves to make a picture. Think of it like super advanced sonar. And then you have MRI, which uses these huge, powerful magnets and radio waves to create just stunningly detailed images of our soft tissues. And over in the radiation corner, you've got the classics. Of course, there's the standard X-ray. Then you've got the CT scan, which is basically a souped-up 360-degree X-ray machine. And then you have nuclear medicine scans, like a PET scan, which are amazing because they show how your organs are actually functioning, not just what they look like. Okay, so let's get into the nitty-gritty. How do these machines actually turn energy into a picture you can see? The science behind each one is pretty wild. For an X-ray, it all kicks off inside a vacuum tube with this little four-step dance. First, a filament gets super hot and releases a cloud of electrons. Then, a massive voltage hits them, accelerating them to insane speeds. They slam into a metal target, and bam! In that sudden stop, X-rays are made. Now here's the crazy part. That whole process is incredibly inefficient. About 99% of all that energy just turns into pure heat. Only 1% actually becomes the X-rays we use. And that's exactly why the target is made of tungsten, a metal with a melting point over 3,400 degrees Celsius, just to handle all that heat. The physics behind this has a German name, Bremsstrahlung. It literally translates to breaking radiation. It's the energy that gets released when those super-fast electrons get braked or slammed to a stop by that target. This is the absolute core of how both X-rays and CT scans work. Ultrasound, though, is a totally different beast. It works on this amazing principle called the piezoelectric effect. There are these special crystals in the ultrasound probe that vibrate when you apply electricity, creating sound waves. Then, when the echoes bounce back and hit those same crystals, they turn the sound back into electricity, which makes the image. So cool. An MRI? Well, that's all about something called nuclear magnetic resonance. You've got this giant, powerful magnet that lines up the billions of tiny protons in your body's water molecules, all pointing the same way. Then, a radio wave knocks them out of alignment for a split second. The machine listens for the tiny signals they give off as they snap back into place, and it uses that to build an incredibly detailed picture. So, okay, the scanners make these amazing black and white images, but how in the world do radiologists read them? Well, it turns out they have a very specific language for talking about light and dark. And get this, something that looks white on an X-ray is called something completely different than what looks white on an MRI. You think white is white, right? Nope. This table right here is basically a Rosetta Stone for medical images. On an X-ray, white is radiopaque, but on a CT scan, it's called hyperdense. It's a whole new vocabulary. Let's just take one quick example. On an ultrasound, something simple and filled with fluid, like your bladder, shows up as pure black. The word for this is anechoic. It literally means no echo, because the sound waves just pass right through the fluid without bouncing back. Simple as that. All right, let's circle all the way back to that first big question about safety. To really understand it, we need to look at the nature of radiation itself. There's this constant trade-off between its power and its potential for harm. When you're talking about radiation, there's a simple relationship that's kind of a golden rule. The better something is at penetrating through stuff, the less damage it actually does along the way. And, the opposite is true too. This right here is the perfect way to picture it. Think of alpha particles like a bowling ball. They're big, they're heavy, they do a ton of damage to whatever they hit, but they're stopped really easily, even by a piece of paper. X-rays and gamma rays, the kind we use in medicine, they're more like a bullet. They're small, fast, and designed to go through the body, which means they do way less damage on their path. So here's how it all stacks up. You can see, in terms of sheer damage, that heavy alpha particle is at the top of the list. But for penetration, the lightweight gamma ray and X-ray are the clear winners, which is exactly why they're so useful for making images. So this all leads to the most important point. When using radiation in medicine, professionals are guided by one simple, powerful idea. It's called the Al-Ara principle. It stands for as low as reasonably achievable. The goal is always to use the absolute minimum dose of radiation needed to get a good, clear picture. You want to make sure the benefit is always going to outweigh the risk. So the next time you or someone you know sees one of these grayscale images, you're not just going to see a bunch of shapes and shadows. You'll actually understand the incredible physics making that picture, the special language used to describe it, and the principles that are always there to keep it safe. The only question is, what new details are you going to see?